Hi everyone, welcome to chapter 14. We are skipping over 13 and we'll go back to it later for anyone in the class this year or in future years that might be taking this course concurrently with AP Calculus BC. There's integration in chapter 13, and if you are enrolled in BC Calculus concurrently, then you may not have completed your integration units yet. So it's the only reason why we're swapping, but it solves that problem entirely. So we're going to dive into partial derivatives. So we're actually going to feel like we're doing calculus now and not just vectors. So here we go. All right, so this is a section that is chocked full of definitions, and I want you to be able to use words intelligently and correctly. So I don't necessarily want to read the whole thing to you, but each time we put up a definition, but I do want to point out significant things in them or maybe words that might be confusing. So the definition of a function of several variables, they propose an idea to build this concept in, and they say, suppose D is a set of n-tuples of real numbers. Okay, n-tuples, that's a weird word. Let me give you a for instance. If you know that n is 5, that is quintuples. If you know that n is 8, that is octuples. If you know that n is 3, that's triples, which doesn't fit the word exactly, but you get the meaning now. So you can have functions of as many variables as you really want to deal with. That's what they're implying with the use of that weird word. Well, we're going to be dealing in real valued functions only, as you have in calculus so far. There is such a thing as imaginary value based calculus stuff. That's the whole realm of complex analysis that if you were to be a math major, you might choose to focus on complex analysis. But in our class, we're doing real valued functions only. And so you see here our W function here. W equals a function of n variables in this case. We're mostly going to focus on 2 and 3, but it is possible to have others. It's hard to draw them once you go outside of 2 independent variables, however. So we have to deal with the concept of domain and range in here, just like in functions you're familiar with in single variable calculus. So in this case, W is the dependent variable and all of the others are independent variables. And you can refer to independent as input and dependent as output variables. All right, my kitty cat likes to get in on the filming. All right, and to sit on my Wacom tablet. Okay, so here we are. We're looking at an XY plane in 2 dimensions, and it's mapping points onto a number line labeled Z, which we know to be the 3rd dimension. We just deconstructed it here. All right, so I like this representation though because you can see the domain. The domain is a set of XY pairs in the XY plane, a region. And those are the independent variables. The range would be the numbers sitting on this number line here. So function of A and B. For this point is AB. There's the Z. The Z equals a function of X and Y. When it's just 2 variables, we call that Z, so that we can use ordered pairs X, Y, Z, when we graph in 3 space. By the way, the symbols, when I say 2 space and 3 space, you have the R. This means real numbers, right? But when you put a 2 up here, it means 2-dimensional space, like the XY plane or the YZ plane, just a plane limited to 2 variables. And when you want to talk about 3-dimensional space, you can use this symbol. 3 space is how we say that. And so those are great ways of writing those ideas in shorthand in your notes or in an explanation in a problem. Those would be great symbols to use. So real numbers would just not have a symbol an exponent type looking symbol up here at all. So 1 dimension, 2 dimensions, 3 dimensions. All right, so functions of 2 variables can take other forms other than x, y, z. So we could have volume as a function of radius and height. If you think about it, that's a cylinder. So what do you think this one is? Area is a function of length and width. What is this one? P is a function of F and A. Pressure is a function of, I don't know, I'm guessing that one. I made it up weeks ago, so I can't remember necessarily. Work is a function of force and direction. E equals a function of m and v, mass and volume. What is E? I don't know. F is a function of m and a, mass and acceleration is force. Okay, so there's lots and lots of concepts out there that are functions of two variables. Here's more than two variables. So our general form is W equals a function of x, y, and z. That was in our definition, but here's a real one. Volume is a function of length, width, and height. So that would be the volume of a rectangular prism or a cube. So lots of applications of functions of multiple variables. All right. So here's some examples of functions that are not applied in a specific situation. So z is equal to the square root of y minus x squared. And our domain is just going to be a description of where at y minus x squared is 0 or a positive number. And then the outputs would be positive numbers including 0. So you can go through these and understand, based on your understanding of functions in one variable, why these are valid. So it's anything you want to plug in for x and y as long as x times y is not 0. You could be more specific. You could say x does not equal 0 or y does not equal 0. And xy doesn't equal 0. You could drag that out, but as long as xy doesn't equal 0, you're good. And then all the output values, well, you'd be able to get anything but 0 as a range value. So you don't really have to change your thinking too much from the past. So down here, same thing, w is the square root of x squared plus y squared plus z squared. Well, since no matter what you plug in, it gets squared and becomes positive, then the entire space, or 3 space, would be your domain for that function, and your output would be all non-negative numbers. So you can think about what you know about the various functions here. Rational functions, natural logarithms, you certainly can multiply them by anything you want, but arguments and logarithms have to be greater than 0, so that holds in 3 space as well. And if you think about the graph of a log in 2 space, you know that it has no discontinuities. It goes in the negative infinity and positive infinity directions forever. And so a surface would also do the same thing when you take the natural log of z. So not too different from what you're used to in the past. I keep reaching for a mouse for my other computer, and I don't need to, so pardon me for that. Okay, so again, definition chock full of words that you need to understand. So if we have a region here, this would be a domain of our function, and this is the region R, and they've isolated a point, and then they've drawn a disk around it. And that is to illustrate an idea they have down here, that a point in a region R in the xy plane is an interior point if you can draw a disk around it. Now, the length of the radius of that disk can be tiny, can be infinitesimally small as long as it exists, and that would make that point an interior point. But if you draw a disk around a point and part of it is outside the region, then that has to be a point on the boundary. So it doesn't have to be a large radius, it can be a teeny tiny radius, but again, part of it lying inside the region and part of it lying outside a region guarantees that that point is a boundary point. So that's kind of how they define things in two-dimensional domains. All right. Take a look down here. They're applying it to a particular region, a circular region of radius 1. And this is the open unit disk is what that is called. They don't call it a circle. So a region is a disk. And again, you see that idea that you could draw a disk around a point, and if every point in that disk lies inside the region, then the point is an interior point. Here, if the function equals 1 as opposed to is less than 1, then it's just the boundary circle, and points would have some inside and some outside if a disk were drawn around them. And then if it says that the disk is less than or equal to 1, it's both the interior of the disk and the boundary of the disk. So pay attention to inequalities and equal signs in these functions so that you can be conscious of whether you need to include the interior or include the boundary in each case. By the way, this interesting notation right here, which we don't spend too much time on set theory anymore in high school, we should. This phrase reads, the set of all points x, y It's this part. This vertical line is such that, and then we just read this as normal. X squared plus y squared is less than 1. So let me repeat that all in one. The set of all points x, y such that x squared plus y squared is less than 1. Now when you read it in sentence form, it makes more sense. All right, moving on. Oh, we shouldn't move on. Look at this. I've got words down here I need to talk about. So they're talking about boundary and open and closed regions. So a region is open or it is closed, and it all depends on what points it's made up of. If it's entirely interior points, it's an open region, and if a region is closed, if it contains all of its boundary points. Okay, so over here on the left, open, over here on the right, closed. Okay, so we want to talk about boundedness. All right, so the disk idea is also playing into this. A region in the plane is bounded if it lies inside a disk of fixed radius. So can you think of things that would be entirely contained in a disk? I can think of like a line segment. Any polygon would be bounded. Points, of course. All right, so those are all things that you could draw a disk around and contain the entire shape inside a disk. But what are unbounded regions? What would those be like? So a region is unbounded if it is not bounded. Isn't that the most ridiculous definition of all time? Okay, that's why I'm talking about this. So lines, of course, extend forever in two directions, so they couldn't be surrounded by a disk. What else? Half planes, planes. They have edges that go on forever. Quarter planes. Those go on forever in some directions and not others. So those would be unbounded regions. All right? I know that's almost silly to have to talk about that, but if I don't, I get questions. Okay, so talk about how to determine the domain of a function. Use the knowledge you already have. Where would you be concerned about a function not existing when it has a square root in it? You know the number under the radical would have to be greater than or equal to 0. Okay, that's one way to describe it. You could also say y is greater than or equal to x squared. All right, let's explore what they said about this in their answer. They drew a picture to describe this. So they said they took this greater than or equal to sign apart, and they talked about it being just equal to 0, which is the boundary, and greater than 0, which is the interior. So the interior of the parabola in the xy plane is the domain for this function. Now, is that domain bounded or no? Well, because the top side has no boundary, this would be an unbounded domain. So it is infinite, but it is not all of R2, okay? So not the entire xy plane, but an infinite portion of it, okay? That's all that really goes into that question. You might think it's more, but it's not. And now we're going to talk about ways of visually representing functions of two variables, okay? So functions of two variables are surfaces, and they can be in 2 dimensions. They don't have to be, or excuse me, can be in 3 dimensions. They don't have to be. I've drawn here in blue and green and red several of the ones we talked about in section 12.6. Here's our, I don't know if you can see my little pointer moving around, so I have to do this. Here's my hyperbolic paraboloid. Here is my hyperboloid of one sheet, and here is an paraboloid, all right? And so getting used to drawing these is kind of challenging, but you need to practice some. I've put a link to a video to help you learn to draw these, and you should watch that video and try to draw a few of them. You don't have to be perfect or great. In fact, like the thing I'm thinking of now is maybe we should put some shading on the underside here. I don't know if that's necessary, but you want to be able to draw one where it looks reasonably good. Not because I'm going to grade you on artistic ability, but because sometimes you just have to visualize something on paper and not just in your head And the one most common application where you're going to have to be able to do that is in setting limits of integration on problems when we get to chapter 15. That's just something that's hard to do in your head, and you need to be able to draw it. All right. Another way we can represent a function of two variables is with, this should say level. Draw and label curves in the plane. Okay, so these are level curves. Okay, so there are graphs, like here. Level curves. We'll take a function. Okay, so let's say we have a function z equals 2x squared plus y squared. Well, this is going to be a paraboloid. It's going to be elliptical, okay, because one axis is longer than the other. And what we're going to do in order to generate curves like this is to say, well, this equals -2. And that's impossible because all these are squared, so we have to use some common sense. So, okay, we can start with 0. And that would just be a dot right here. We could say it equals 1, and then we could graph that ellipse, and then we could say it equals 2, and we could graph that ellipse, and we get to choose. Now, if you skip around a lot, your picture's not going to be pretty, but here's the kind of picture you would get. And my question for you is, why are some of these curves closer together and some farther apart? What do you think about that? Well, this indicates that these curves that are closer together indicate a steeper rise than the curves that are farther apart. So the bottom of the bowl is less steep in its rise from the origin, where it's the lowest point, till it gets to this first curve, would be a gradual increase, whereas the sides of the shape would start to be more slanted, a steeper rise, or increasing more quickly, if you will. So this is one way to represent, if you do a lot of lines using consecutive integers, you get this sense of how far apart the curves are, and it tells you where the steepness comes into the picture. Now, look at the middle one here. What shape do you think that might be? Well, these in one direction could have a curvature going up, and these could have a curvature going down. So this could be a hyperbolic paraboloid. What do you think about this one? This one is not a function, one of our standard quadric surfaces that we studied, but what do you think these little closed curves represent as opposed to open ones like in the middle drawing? So I think these would represent hills or valleys, and the littlest circle on the inside or littlest curve on the inside would be the very peak or the very bottom of the valley. All right, so setting a function equal to a constant and a series of constants would enable you to draw level curves. So graph this function, 100 minus x squared minus y squared, and plot the level curves 0, 51, and 75. Now, the fact that they skipped around a bunch means that you're not going to get a sense of the steepness of the curvature of the graph, but how can we do this? All right, so first we've got to do function of x and y equals 0. So that's going to be 0 equals 100 minus x squared minus y squared. So we're going to turn that into x squared plus y squared equals 100. Okay, well, I can draw that. That's a circle at the origin with a radius of 10. Okay, so here we go. If I make a radius of 10, here we go. I always make these tick marks parallel to the x-axis to give me a sense of 3D-ness. Okay, and of course you can draw the other axes, so that would be -10, that would be -10, and so here's a circle. I did not draw it to scale very well, but we're looking at it from a slant. So if we were looking at it from above, here it is from above, we would have 10, 10, 10, and 10, and despite the sadness of my ability to draw a perfect circle on a Wacom tablet, that's what it would look like from above with the x and y planes. Okay, well, then we need to deal with this function equals 51, so we take 51 equals 100 minus x squared minus y squared, and then we get x squared plus y squared equals 49. So this is a circle of radius 7, so we could come in a little bit. And we could draw, you see now why they chose particular numbers up here. And then if we do 75 equals 100 minus x squared minus y squared, we're going to end up with a circle of radius 5. So we would have a smaller circle in here. All right, and if we translate these over here, that would be 7, circle there. I'm not so bad with a pencil and paper, but with a Wacom tablet, I'm terrible. All right, so yeah, I've definitely got that one out of scale. Okay, so circle of radius 5. And you might just come in here and say 5, 7, 10 to provide scale for folks. And based on this, and knowing in general that the shape is a hyperbolic paraboloid, but these are points somewhere on the curve at various levels, this is going to end up being, if I have x and y are 0, then our function value is going to be 100. So that's going to be a peak. So this gives me a way to draw the parabola that's going to help me see this shape in general. Okay, so I can try and provide some of the curvature in the picture with some curved lines. I know that a number of you are art students and you're really good, so you're not allowed to laugh at me for this, okay? I'm not an art student. I'm not particularly gifted in drawing, but I can draw enough curved lines for you to get the sense that this is an inverted paraboloid, rather. So this would be the level curves. This would be the actual graph of the function, and these on the right would be the level curves. And you certainly could do more of them, but they just asked you to do 3. Okay, so there is an example of drawing. Here's the perfect pictures, okay? They did the level curves mixed together with the graph of the inverted paraboloid, and it looks much better than mine. But the point is, when you cut through this shape with a plane at the various levels, then you get this shape, which they then project down onto the XY plane. And so you chop it in various places, and then you get the multiple level curves. All right, so this dot comes from running the plane, so it just hits z is 100, and then you have 3 other places that it hits. Okay. So, oh, by the way, be mindful that as this paraboloid extends down below the xy plane, it does continue to widen to infinity as it goes down. The only way you could stop that is to limit its domain. All right, so in real life, these are examples of level curves that I took from the internet. And they are maybe familiar. Maybe you've taken science classes where you had to deal with this kind of data. But I want you to kind of look at, this is the map of some terrain, some ground. And you can see where they've listed elevations. So this is at 11,600. I don't know what the scale is, feet, meters, who knows. But you can see some of the curves are closer together. That means this portion here would be steeper than this portion here. If you were going to try and climb this, this is the peak of a hill. And that hill has got this odd shape when you look at it from above. If you become really good at this, you might be able to tell where water flow would be. Now over here, a contour map. Surfer is not, this is not referring to surfing. This is a technical term for people who make and use contour maps. I think it might even be the name of a software program. But this is showing you different numbers here in areas that correspond to these numbers. And since there's no more information, we can't really know what this is for. But here we go. We've got Oneida Lake up in New York. It says this is a depth, a measure of depth. So, and they've got, I think these might be latitude and longitude numbers on the horizontal and vertical scales. And then the colors are representing temperature. Oh, temperatures, not depth. Okay. Although I would imagine the deeper you go in a lake, the colder it is. So they do have temperatures down here. They didn't indicate Celsius or Fahrenheit, but blue would be the most frigid down here at the deepest point. in the graph, and then red would be the shallowest, where the warmest waters are. And so these are very, very helpful, useful, commonly used representations of real life things. Okay, so you don't have to be limited to 2 variables. Once again, we've got this idea of functions of 3 variables. So the set of points x, y, and z that has a constant value, okay, the set of points where a function has a constant value here, they write it like this, the function equals c, is called what? You don't have level curves for a function that is essentially 4-dimensional. You can't draw it 4-dimensional, but this is the best you can do drawing a 4-dimensional object, is to draw a set of level surfaces. Okay, so 3-dimensional surfaces, that is what you render a 4-dimensional curve down into in order to be able to render it in any sort of way visually. All right, so describe the level surfaces of this function. So we've got the square root. This looks like, so this would be, if this were equal to a constant, this would be a sphere, and the square root would just be positive portions of it. And so if we set this function equal to various integers, doesn't have to be integers, but they're easiest to deal with, then we get a set of spheres, and this part has to be positive. So, but it doesn't, since all these terms are squared, we're not limited in our domain, so we can include negative x, y, and z values in that as well. And so each shell is a different integer. So the outer shell here is, oh, gotta draw, is when the function equals 3, and the outer shell, or the inner shell here is where it equals 2, and this tiny little shell is where it equals 1. You could set it equal to 0, you would just get the point at the origin. So you can also represent functions of 3 variables as level surfaces, but it's the closest you're going to be able to get to drawing them. All right, so again with the definitions, but this time we've moved up in our numbers of dimensions. So we have a region in space, okay? We're going to call that region R in space, and they're defining an interior point and a boundary point in a similar way. So if you can pick a point in a region and draw a sphere around it, no matter how small the radius is, as long as the sphere is entirely contained within the region, that this is an interior point. And if the sphere is partially in the region and partially out of the region, then you have a boundary point. So very similar definition as before, but raised up into space instead of limited to 2 dimensions. Again, they bring up a region is open if it's just interior points, and closed if it contains its entire boundary. Okay, so very, very similar to before. Now, we want to try and learn to match together functions with their contour curves. So the answers at the bottom are jumbled, but the answers are underneath the blue rectangle. So take a moment and pause it and look at these and just tell me which contour chart goes with which function. Okay. So hopefully you pressed pause and thought about that for a moment. And let's see if you got this right. So let's look at A. A looks like a piece of an egg crate where you might store eggs. And if it went on forever, you'd see more than just 2 peaks, because we've got a peak here and we've got a peak here. And if we continued in the negative y direction, you'd see a peak here and a peak here, because it does get the same color. So that is the top, but we can't see where it goes back down the other side. You know, this would continue. If they made the domain of this function the entire xy plane, then this would just be like very orderly mountains and a bunch of different peaks. So this one just has this peak, and this kind of spot. We're not sure whether that's up or down without looking at the actual function. We have a bunch of peaks here, and they're going to continue. You can see hints of it on the outer edge where it's continuing in the same manner. And we don't see any closed curves here, so there's no actual peaks. So I'm going to say that this one is A. All right. Then this one right here has 2 specific peaks and a low spot in the middle, so that corresponds to this one with a peak here and a peak here and a low spot here. So I'm going to say that's B. Now, by process of elimination, this has to be C, but let's make sure it feels right. So we don't really have peaks on this graph. We have hills that build to a certain point, and I get the impression that it would continue like this forever, that this ripple right here would continue to get taller, this one would continue to get lower, and these would level out on either side. So here we see those ripples. We can't tell from a contour plot whether this is an upward ripple or a downward one. So one of them goes up, one of them goes down, and we only know that because we've seen the graph. What we know from the graph is when this one goes up, this side goes down, and vice versa on the bottom. If this side goes down, this side goes up. So this one is going to be C, and I can feel good about those answers if I check them. There's C, there's Z, and there is B. Excuse me, C, A, and B. And it is kind of interesting to look at these to see what equations produce these answers. So our ripple thing here is, it's got an exponential function in it. It's got x and y multiplied with that exponential function. A trig function, is not really surprising that it creates an egg cart because you can see, don't mean to be picking these up, I need to draw on them. You can see the trig sines and cosine waves in the cross section of this curve. And then over here, this by itself, would be a hyperbolic, would be a paraboloid. This is this element, the exponential element in there with kind of an interesting exponent, limits it to just 2 peaks, and then the surface levels out, and I imagine is what's the word I'm looking for? Asymptotic to the xy plane. So you can't necessarily be expected to memorize equations of every single form and know what they're going to look like in 3 space. But if you think about the equations and what's in them and what you know about those graphs in 2 dimensions, you can usually match them up pretty well, whether you're given contour maps or equations or what have you. All right, that's all for lesson 14.2. Thanks for listening.